Welcome to the deep dive. Our mission, as always, is pretty straightforward. We wade through all the source material, cut through the noise, and give you the essential knowledge you need to be totally up to speed. Today, we're doing a really critical deep dive into the GTC 2025 conference sources. We're zoning in on the CEO keynote, specifically what it tells us about where AI and computing infrastructure are headed, like, right now.
Yeah, that event was back in D.C., mostly October 28th and 29th, 2025, right after some workshops. And, looking at everything, they put out the papers, the talks, it was broad, really broad.
What kind of things?
Oh, everything. Physical AI,
Yeah.
Robots and stuff.
Yeah.
Agentic AI, remote sensing data, HPC, obviously. And interestingly, some big steps in quantum computing, too.
Okay, so a lot going on. But if we boil all that down to one key takeaway for you listening, it's this. Computing isn't just getting a bit faster. It feels like we're in the middle of not one, but two huge platform shifts at the same time.
Exactly. It's a fundamental change in how we build and use computers. And it's unlocking these, radical performance jumps that are basically rewriting economic possibilities.
Right. Let's unpack that. Maybe start with the problem. Why did we even need this massive change?
Well, the sources really hammer this point. General-purpose computing, the kind we've relied on for decades, essentially hit a wall. We all know Moore's law, right? More transistors.
Sure, doubling every couple of years.
Yeah, but the benefit of that, doubling the actual performance boost and power savings per transistor that stalled out maybe nearly a decade ago.
Oh.
They specifically mentioned the end of Dennard scaling.
Dennard scaling, remind me.
It was the principle that let designers shrink transistors and lower the voltage proportionally. So the power density, the heat, stayed manageable. When that stopped working, CPUs just couldn't get much faster or more efficient without melting, basically. Physics and cooling became the hard limits.
Okay, so the old way, just making the main processor faster and faster sequentially, that hit a dead end. So what's the alternative they pushed?
The alternative is accelerated computing. The sources call it the first really new computing model in something like 60 years. It's a hybrid. You use the parallel power of the GPU alongside the sequential CPU. It lets you work around those physical limits and just do way, way more.
Parallel versus sequential, that seems key. But the sources also stress something else, that the hardware is only part of it. They call the programming model CUD the real treasure. Why focus so much on software that's, 30 years old?
Because that consistency is everything. Think about it. They're moving to CUDA 14 now. But the core point is it works across hundreds of millions of GPUs across different generations. Developers don't have to scrap their code every time a new chip comes out. That's huge.
Right. It creates a stable platform. And it's more than just the base layer, right? There are all those libraries.
Oh, yeah. Over 350 CADX libraries. These are like specialized toolkits for specific applications. They accelerate particular kinds of work.
Any key examples stand out?
Definitely. They highlighted Calitho. That's for computational lithography. It's what TSMC, Samsung, ASML, the big chip fab players use to actually design and optimize the chip manufacturing process itself. So using accelerated computing to build more accelerated computing. Then there's MONAI. It's apparently the world's #1 framework for medical imaging AI, helping doctors analyze scans faster, more accurately. And Quantum, which provides the tools needed to link classical supercomputers with emerging quantum processors. Really critical stuff.
Okay, so accelerated computing fixed the physics problem, how to keep performance climbing. Now let's pivot to the economics. AI seems to have completely changed the game there. The sources say AI is work, not just a tool. Why is that distinction so important?
It's fundamental. A tool, like Excel or Word, it just sits there. You use it when you need it. Its market is limited by what companies spend on IT, maybe $1 trillion globally, something like that. But AI is active. It can augment labor, make decisions, generate output. It acts like a worker. That means it can tap into the entire global economy, which is closer to, $100 trillion. Yeah. It's a totally different scale. And serving that scale needs new infrastructure.
Which brings us to the AI factory. Okay, when I hear data center, I think servers for email, websites, databases, kind of a mix of everything. How is an AI factory different?
It's completely different in purpose. A traditional data center runs lots of different apps. An AI factory is designed really to do one main thing: run AI. Training huge models, running inference, doing what they call AI thinking.
Thinking?
Yeah, like complex problem solving using the trained model. The factory's entire goal is to produce the basic unit of AI, value the token as efficiently and cheaply as possible. And because we're hitting those limits with Moore's law, getting the needed 10x, 100x gains requires something called extreme co-design.
Extreme co-design. Okay,
Yeah.
What's that involve?
It means you can't just design a better chip in isolation anymore. You have to reinvent everything together from scratch.
Yeah.
The chips, the systems they go into, the networking, the power, the cooling, the software stack, the AI models themselves, even the final application, all co-optimized.
That sounds incredibly complex and probably expensive. But the results they claim are pretty staggering. The Grace Blackwell NVLink 72 system, they're saying 10x better performance per GPU than the H200. But the bit that jumped out at me was the claim about costs, the lowest cost tokens in the world driving costs down 10x. How is that even possible?
Comes back to that extreme co-design and integration. They're not just selling individual GPUs anymore. They're selling a whole integrated rack-scale computer optimized purely for AI. By pushing efficiency in power, cooling, data movement at the system level, they dramatically lower the operational cost to produce those tokens.
So it's the total package, not just the chip speed.
Exactly. And this is scaling fast. The Vera Rubin system is the next generation, the third gen of this NVLink 72 design. They said it's capable of 100 times the performance of the DGX1 they sold to OpenAI just 9 years ago.
100 times in 9 years. Wow.
Yeah. And the description was vivid. It's apparently completely cableless, using advanced silicon photonics for chip-to-chip communication, and it's 100% liquid-cooled. It's not just a server rack, it's a highly specialized AI production machine.
Okay, so they've basically reinvented the computer inside the data center. They solved the physics for making tokens efficiently inside the factory. Where do they point that power next, outside the building? The sources mentioned 2 big new platforms, starting with 6G.
That was the first big external platform push, yeah.
Yeah.
They frame 6G as a major opportunity, especially for the U.S., pointing out how much current wireless tech relies on foreign suppliers. The idea is to build an AI-native wireless standard here.
And the product is NVIDIA ARC, Aerial Radio Network Computer.
That's the one. It's a full system, Grace CPU, Blackwell GPU, ConnectX networking, all running a specialized software library called Aerial CUDAX, basically applying their accelerated computing model to the massive computational task of running a modern wireless network.
And the key partner here is Nokia.
Right, Nokia, number 2 in telecom equipment, tons of 5G patents. They're integrating ARC. And this enables 2 really interesting concepts. First, AI for RAN.
AI for the radio access network, what does that do?
It uses AI, things like reinforcement learning, to make the network way more efficient at using the available airwaves spectral efficiency. Getting more data through the same spectrum. Why does that matter? Because running the world's cell networks uses a huge amount of power, like 1.5% to 2% of all global electricity. AI can help cut that significantly.
Okay, efficiency. What was the second concept? AI on RAN.
Yeah, and this one feels even bigger. AI on RAN basically turns every cell tower, every base station into an edge computing node. So it's not just passing data through, it's processing AI workloads right there at the edge. Think industrial robotics, autonomous systems. It pushes the AI factory right out to where the action is.
It's extending the factory to the edge. Okay, from global networks down to quantum, that seems like a leap. How do you integrate this kind of architecture with something as delicate as quantum computing?
Well, the timing seems right. The sources talked about a major breakthrough after like 40 years of work. The industry can finally create one stable, error-corrected logical qubit. That's the usable unit you need. But making one requires tens, maybe hundreds, of noisy physical qubits all working together, constantly being monitored and corrected by classical computers.
Ah, so the quantum part needs a really fast classical computer just to keep it stable.
Exactly. The quantum state is incredibly fragile. So they introduced NVQLink. It's a new, super-fast interconnect designed specifically to link quantum processing units, QPUs, directly to NVIDIA GPUs. The GPUs handle the intense real-time error correction, the calibration, the control needed to keep that logical qubit alive.
And they made this an open platform, CUDA-Q.
Yeah, CUDA-Q. It extends the familiar CUDA model to include quantum. And the uptake seems significant. They listed, 17 quantum companies, 8 major DOE labs, Berkeley, Fermilab, Oak Ridge, all jumping on board. It looks like a real effort to standardize how we link classical and quantum systems.
Okay, so we have the AI factory, extensions to 6G, links to quantum, and let's connect it back to the physical world. Physical AI. AI that needs to understand physics, cause, and effect. The sources mentioned a specific 3-part pipeline for this.
That's right. 3 distinct computers needed. First, the GB200 systems for the massive training of the base models. Second, the Omniverse computer for simulation, creating the digital twin environment where the AI learns physics safely. And third, the Thor Jetson robotics computer. That's the chip that goes into the actual robot or vehicle for operation in the real world.
Let's dig into that simulation part. Omniverse DSX, the digital system exchange. It sounds like more than just software, almost like a factory design tool.
It really is. Think of it as a blueprint and simulation platform for designing and operating these huge gigascale facilities like the massive AI factories themselves. Partners like Jacobs Engineering and Siemens are using it to model everything density, power, cooling, workflow before building. Optimizing in the digital twin first saves potentially billions in the real world.
And we saw real-world examples of this physical AI taking shape. Foxconn using Omniverse to simulate and train robot fleets for new factories in Texas.
Yep. And in humanoid robots, companies like Figure and Agility focusing on warehouse tasks. Johnson & Johnson using it for advanced surgical robotics. Even that simulated Disney robot demo showed the potential.
Right. And then mobility. The NVIDIA Drive Hyperion platform. It's like a standard kit for building robotaxis.
Pretty much. A reference architecture sensors, compute, chassis integration points designed for autonomous driving readiness. And quite a few automakers are adopting it. Lucid, Mercedes-Benz, Stellantis.
But the big news seemed to be the Uber partnership, connecting all these future Hyperion-based cars into Uber's network.
Exactly. That connects the vehicle hardware standard with the massive existing ride-sharing network and logistics. It potentially accelerates the deployment and market access for these autonomous vehicles significantly.
Okay, one more connection before we get to the financials. Enterprise AI. We sort of skipped over some key partnerships there. How's this architecture changing things for businesses?
The theme seems to be enabling AI to work at much higher speeds and on more complex real-time data. Take CrowdStrike, the cybersecurity company.
Right.
They're partnering to build high-speed cyber AI agents. The idea is AI that can detect and respond to threats at machine speed in microseconds because human analysts just can't keep up anymore. The new compute power enables that kind of speed.
And the Palantir partnership, accelerating their ontology platform. What does that mean for users?
So Palantir Ontology is basically their system for creating a digital model of a complex, real-world environment, mapping out relationships between data points like in supply chains or organizations or intelligence scenarios. Accelerating it with Blackwell means customers can process vastly more data, connect more dots, and get insights much, much faster. It enables real-time, large-scale decision-making on messy data that just wasn't feasible before.
Okay, makes sense. Speed and scale for enterprise data. So we've seen the tech, the platforms, the applications. Let's talk money. The sources describe this powerful economic cycle driven by two exponentials.
Exactly. It's a virtuous cycle. First, you have the exponential demand for compute power to make AI models smarter.
Yeah.
They broke this down into pre-training, post-training refinement, and then what they called thinking.
Thinking again.
Yeah. Using the trained AI to actually solve novel problems. That thinking phase is becoming computationally very expensive. The second exponential is usage, because these models are getting so capable, they're becoming worthy to pay for. People and businesses will pay for what they can do.
More demand for smarts, more usage because they're smart.
Right. It feeds itself. This dual pressure means the need for AI compute just keeps climbing, eventually exponentially, for a good while.
Which brings us to those staggering numbers. They mentioned visibility into $500 billion. That's $500 billion in cumulative Blackwell and early Rubin system business booked through 2026.
$500 billion, yeah. And get this, that number excludes China and Asia. Even without those massive markets, it represents something like a 5x growth rate compared to the Hopper generation.
5 times the growth rate of the previous generation, even excluding huge markets. What does that signal to you? Is this the big inflection point?
It really signals that the market, big enterprises, cloud providers, sees building out this AI factory infrastructure, not as some future maybe, but as an urgent, immediate necessity. The capital is flowing because these systems are viewed as essential production tools needed right now.
And there was a strong theme about where these tools are being built, tying into U.S. reindustrialization.
Absolutely. They were very clear about this. It's presented not just as a business choice, but a strategic one. Blackwell manufacturing is deliberately happening in the U.S. Silicon from Arizona, the advanced HBM memory from Indiana, rack assembly in places like Texas and California. They're consciously branding the AI factory age as being made in America.
Linking compute leadership directly to domestic manufacturing. That's a significant statement. Okay, so this deep dive really underscores a massive shift. We've gone from accelerated computing, providing better tools, to enabling AI workers, and now building entire AI factories designed for this new era of exponential demand.
Right. And maybe the final thought for you to consider, tying back to that idea of the AI factory, its core product is the token. We heard tokens can represent language, images, code,
Mm.
but also 3D structures, chemicals, proteins, even genes.
Mm.
The whole economic engine is now geared towards making these tokens cheaper and more abundant.
Okay.
So think about this. What happens when these AI factories start churning out tokens that represent the fundamental laws of physics or the deep structures of biology or maybe even patterns in the universe we haven't grasped yet? What entirely new scientific languages might AI unlock and teach us next once producing those insights becomes the primary output?
That's a profound question to end on. What language will AI teach humanity next? We hope this deep dive into the GTC 2025 sources has given you a solid grasp of the huge changes underway in tech and the economy. Until next time, keep exploring.